Assalamualaikum warahmatullahi wabarakatuh. My name is Akmal Azraei, B1 NAZLI. My number metric is B0922102112. Our mission is optimize heat transfer in solar water heater using simulation-driven analysis to advance sustainable energy. So, first slide. Solar water heater converts solar energy into thermal energy using collector. Key component is solar collector, storage tank, and circulation mechanism. Efficiency depends on material property, solar intensity, and heat transfer mode, conduction, convection, and radiation. So the second slide, our goals focus on key component. The transparent cover that trap heat, and second, solar radiation absorbed by the collector. The third, a cool water inlet feeding into the system, and insulation layer reducing heat loss. So the fourth slide, the working principle involve the one, solar radiation absorbed by the collector. Second, the conduction transfer heat to water. And third, convection moving heat water to the tank and minimizing radiation loss via insulation ensure solar gain exceed heat loss for optimal efficiency. So in the top view, you see the serpentine tube layout maximizing surface contact between absorber and water. So the critical labels are first, transparent cover, and then second, absorber plate, third, flow tube, inlet outlet mark. For insulation layer, the isometric view reveal layer construction, glass cover, absorber tube, assembly, and then back insulation. The final is structure frames. So the mentioned call out show 20mm a gap between glass and absorber for convection suppression and 75mm side insulation thickness to prevent edge conduction loss.
Seterusnya, saya Muhammad Ashraf bin Muhammad akan menerangkan tentang teori calculation. Untuk ia bermula dengan conduction melalui collector panel. Untuk conduction terdapat 3 formula, iaitu conduction daripada plate, mana formulanya adalah K darab A darab perubahan suhu dengan thickness D. Kemudian formula yang kedua adalah conduction cylinder, iaitu perubahan suhu bagi resistance cylinder. Untuk mencari resistance cylinder, formula dia adalah ln R1 bagi R2. R1 adalah outer diameter, R2 adalah inside diameter, bahagi dengan 2 pi darab length darab thermal conductivity. Slide yang seterusnya, untuk explanation tentang teori conduction ni, dia bermula daripada absorber plate, iaitu daripada surface kepada flat copper plate, keseluruhan flat copper plate yang menggunakan Fourier's law for one dimension steady state conduction. Kemudian untuk formula yang kedua, second conduction, dia heat flow daripada bottom absorber plate kepada cylinder copper pipe wall. So ini akan menggunakan conduction cylinder dan resistance cylinder punya formula. Jadi ini adalah teori calculation yang telah kami buat. Dan thermal conductivity untuk suhu ini adalah assume saja. Yang seterusnya adalah teori convection. Ini adalah formula convection, iaitu Q convection sama dengan HA darab dengan TS tolak T infinite. Jadi di sini ada simbol dan dia punya maksud, dan explanation ni adalah daripada inner wall kepada fluid inside. Jadi dari teori ini adalah teori calculation yang telah kami buat. Itu 30,800 watt. Itu sahaja daripada teori kami. Sekian, terima kasih.
Our summary of the theoretical result at 70 Celsius absorber temperature and 30 Celsius temperature ambient under 800 watt meter per square solar flux. Our thermal analysis reveals conduction loss through bottom outside insulation is 101 watt, convection loss from the top surface total 432 watt, and then radiation loss is only 66 watt. So this yield 980 watt useful heat gain, achieve 53.1% system efficiency. So this result validate our design exceptional heat retention. Thank you.
So I will present for slide design model. So this is the design model used for our simulation. It represents the structure and key components of the system, including the flat plate and copper piping. The purpose of this model is to study the thermal performance under solar exposure using CFD tools. So next is simulation setup, CFD modeling and meshing. So we begin by developing a CFD model to stimulate heat transfer and fluid flow within the system. Meshing was done to divide the model into small, manageable elements, which is critical for solving the governing equations with better accuracy. A finer mesh typically leads to more precise results through it increases computational time. So for the next slide is simulation setup. Sunlight conditions. So the simulations assumes constant direct sunlight with the intensity of 900 watts per square meter. The site is the Faculty of Mechanical Technology and Engineering located in Melaka at coordinates 2.2795 north and 102.2737 is we set the sunshine factor to 1, representing maximum exposure to sunlight. The solar irradiation value used was 800 watt per meter squared, accounting for realistic energy input into the system. So for simulation setup, material properties. In the setup, multiple materials were used which defined by specific thermal properties. So for the copper, high thermal conductivity, which is 390 watt per meter Kelvin, ideal for heat transfer. For stainless steel, moderate conductivity and higher specific heat. And glass and insulation were used for thermal containment and transparency. Water as the working fluid has a high specific heat of 4182 joule kilogram per Kelvin, suitable for absorbing and transporting heat. So the next one is boundary conditions. So for boundary condition were carefully defined to simulate real operational conditions. For inlet, mass flow rate set at 0.001 kg per second with an initial temperature of 25 degrees Celsius. So for the outlet, set to a backflow total temperature at 55 degrees Celsius. The flat plate used a mixed thermal condition with a heat transfer coefficient of 120 watt per meter square Kelvin. Free stream temperature is 25 degrees Celsius and external radiation temperature is set to 28 degrees Celsius. The copper pipe surface was defined with a constant heat flux of 800 watt per meter squared. All solid walls were assigned a uniform thickness of 0.001 meters. So next is run calculation. The simulation was executed for 1000 iterations. This was sufficient to achieve a converged solution and observe the thermal response of the system under steady state solar loading. Temperature distribution from experiment. Based on experimental data, the inlet water temperature was 10.12 degrees Celsius and the outlet temperature was 10.27 degrees Celsius. Although the change appears minimal, it provides a measurable indication of energy absorption. In practice, optimizing material choice and boundary setups could improve heat gain significantly.
Results of operation. So the simulation of the solar water heating system conducted using software like ANSYS Fluent or SolidWorks flow simulation. So which it provides for the system performance. So it can show a clear temperature gradient from the absorber plate to the outlet, confirming efficient heat transfer. So all the heat transfer modes, which is conduction, convection, and water flow and radiation process, were visible and aligned well with theoretical expectations. So overall, the simulation results closely match theoretical expectations with differences under 10%, mainly due to the simplifying assumptions in manual methods. So summary table for heat transfer mode. So as you can see, there are three modes: conduction, convection, and radiation. In the end, we will get the theoretical result, simulation result, and differences, which is a bit similarity, and light, which is conclusion. Okay, in this slide, this analysis compared theoretical and simulation results to evaluate heat transfer in a solar water heating system. Both methods showed efficient conduction, convection, and some heat loss by radiation. Simulations confirmed the theory with slight differences due to the ideal assumptions like uniform solar input and perfect insulations. Overall, the results validated the design and highlighted ways to improve efficiency, supporting the move towards sustainable energy solutions.